So hello everyone. We are going to start with section E in this particular video, and so E1, that is atomic physics. We are going to cover only SL part in this video. So first is the structure of atom. When we talk about structure of atom, it starts with Dalton, who described atom as individual part of matter, and but that was not so be scientifically backed. But there was discovery of electron, which was done by J.J. Thomson, who proposed the plum pudding model. A plum pudding model suggests that there is a positively charged sphere and on which you can see there are electrons which are just like a choco chip in a cookie dough or like a plum in a pudding. So this model was the first actual model we had which had some scientific backing to it because the discovery of electron supported that. But there was a lot of failures to for the multiple elements, how those electrons are staying together, and all those questions were raised. Then after a few years, Rutherford with his associates Geiger and Marsden developed an experiment for gold foil scattering. In that experiment, they set up the gold foil, which was extremely thin. And gold has that property of being ductile and malleable, so that we can produce a thin sheet, which is few atoms wide, and we can bombard that sheet with alpha particles. So before Rutherford doing this experiment, there was a radioactivity discovery, and we discovered all the alpha, beta, gamma particles. So alpha particles being positively charged and released from a radioactive source can be accelerated using some potential difference and electric field. So we had a beam of alpha particle hitting the gold foil, and we had a photographic screen which could detect any alpha particle. And because of that, what few observations were made in this experiment. The first observation being most of the alpha particle went straight through the gold foil. Now, that suggested Rutherford to think of a model where if the most of the alpha particles are going straight through and not interacting with anything else, it means the atoms is mostly empty, not like a positively charged sphere, what Thomson proposed. Because if it was a positively charged sphere, then definitely alpha particle being positively charged, there would be some kind of interaction, but there wasn't. So he suggested that atom must be empty. Most of the atom must be empty. Second, this was the observation. Some of the alpha particles were deviated for angle less than 90 degrees, and extremely few alpha particle got deflected angles that are greater than 90 degrees. Now, those two observations suggested Rutherford to develop a model where he suggested that the atom is mostly empty and all the positive charge is being concentrated at center within a tiny space that is called nucleus. So he proposed a term nucleus where an atom has a very small tiny part which is positive at the center, because of which there are slight deviation when the alpha particle came close to the nucleus, and when the alpha particle had a very head-on collision with the nucleus, it showed angles greater than 90 degrees as a deviation. Also, the electrons must not be moving randomly, because if there is a positive atom at the center, obviously the electrons will accelerate towards the center, which wasn't there. There was no radiation coming, because whenever an electron accelerates, it radiates. So there was no radiation coming out. So he suggested the electron must be orbiting the nucleus, like how the planets orbit a sun, even if there is an attractive gravitational force between them. So he suggested the electron must be orbiting, and because a stationary electron will accelerate towards the nucleus and radiate energy, which was not observed. Okay. During that time, we have to be very careful. There was no protons and neutrons were discovered. So this is like a common questions they ask in MCQs to confuse the student. But we have to remember the history. There was no protons and neutrons discovered at the time of this experiment. Then after 5-10 years, Bohr was developing a model where he saw a spectrum of hydrogen gas, and which encouraged him to develop a model. So what he suggested that the electrons must not be moving in a random orbit, but all those electrons must be orbiting the nucleus in a very definite radii. Okay, each orbit describes a discrete energy level, and in all those orbit, electrons do not radiate. So, like a planet that can orbit a star at any random radius, here it is not possible for the electron. Electron only can have a fixed energy around the nucleus to orbit in a way that it does not radiate or does not accelerate. Okay. Yes, there is an acceleration due to circular motion, but that is an equilibrium and it is going without changing its energy. Okay. So those fixed energy points are discrete. It means they are fixed. So you can jump from this to this level only. Then electron can't stay stable in that between any of those energy levels. So those are the first thing that he suggested. Second thing, when an electron gains or lose energy, it can make a transition between the energy levels. Okay, so when I refer to energy level, I am trying to say that it is an orbit around a nucleus which is of a fixed radius. Okay, so when an electron makes a transition from higher to lower level, it emits a photon that has energy equivalent to energy difference of the level. Okay, so this is the more important part, because this is where the observation that he made for the hydrogen gas supported his statement, because what he saw is that hydrogen gas emits some light when subjected to extremely high electric field. Now that light, when he observed, it has specific wavelengths associated with them, and then those specific wavelengths suggested that there is a photon of specific energy levels which has to be equivalent to the difference in the energy levels of the transition. So that was the two observations that Bohr made, and this was very successful model, because of this we can make sure all the elements have their different number of electrons, and all those electrons are orbiting the nucleus in different shells, and which makes some elements more chemically active, some elements less chemically active. So all this chemistry was very intriguing and very easily explained using Bohr model. Then we had some uncertainty principle from Heisenberg, who said that the electron position cannot be position and momentum cannot be determined simultaneously. There is some kind of uncertainty in both of them. When we try to figure out when the uncertainty of the other increases. So, and then we also saw that, like particle nature of light, there is also a particle nature and wave nature associated with the any particle like electron. So instead of electron being orbiting a nucleus in a single orbit, we suggested that it is like a wave function, okay, and makes a standing wave like this that I have shown it. The position of the electron about the nucleus is not definite, but we rather represent it using a wave function. So wave function which gives a probability of electron to be at certain position, not the exact, but a probability is what we use. So that is a Schrodinger model. And what is now accepted today is Schrodinger model. Okay. Now we will talk about basics of how the energy of the electron is calculated. So energy of a photon is calculated. Energy of the photon is related to, can be calculated by HF or Hc by lambda, where H is a Planck's constant, which is given as 6.63 into 10 raised to minus 34. It is given in data booklet. And F is the frequency of a photon. The photon is a massless particle of light. It is basically an electromagnetic wave, but a particle form of an electromagnetic wave. Okay. And wavelength, lambda is the wavelength of a photon. C is the speed of the light. We know speed of the light is 3 into 10 raised to 8. Okay. So if I substitute H in values of this 6.63 and frequency in terms of Hz, we will get our energy in terms of joules. But what you will find in this chapter, most of the energies are given in electron volt as a unit rather than joules. So we need to probably know the conversion from the joule to electron volt. So this is the conversion. You have to divide it by 1 by 1.6 into 10 raised to minus 19. That is an elementary charge. So to get the value in joules, okay, and you can do vice versa. You can multiply by 1.6 into 10 raised to minus 16 to convert electron volts to joule. Okay, that conversion is necessary also. But you will find in most of the questions, instead of giving you frequency, they will rather give you a wavelength. Okay, so when they give you wavelength, what you need to do is you can substitute value of HCA, which is given in data booklet as 1.99 into 10 raised to minus 25. Now this is something that you will do if you want your energy to be in joules. But as mostly asked, the energy is calculated in electron volt. So what you do, you substitute, instead of separately substituting value of H and C, you substitute 1.24 into 10 raised to minus 6. You will directly get the value of energy of a photon as in electron volt. So you don't have to convert again later on. Okay, so those are the conversion factors which are given in data booklet. You can use it. Okay, so this is how we calculate the energy of a photon. Now there are two kinds of transitions that are possible. Either it is an absorption or it is an emission. So in absorption, electron jumps from a lower energy level to higher energy level by taking some energy from the incoming photon, or it can be any collisions also can make an electron jumps to higher energy level. That is also possible. In emission spectrum, electron jumps from higher energy level to lower energy level while emitting a photon. So that's why it is an emission spectrum. In both the scenario, what is important to remember, the energy of this photon, whether it is absorbing a photon or whether it is emitting photon, it has to be equivalent to the difference in the energy levels. Okay, those are the photons that we observe in a spectrum. Okay, what is a spectrum? How do we create it? We will discuss this just in this video later on. Okay, so if I use the energy of the photon and relate it with the difference in energy level, so you will get a relationship like this, and then we can relate this wavelength of the photon with the energy level. Now you can see that the wavelength is inversely proportional to the difference in energy level. So higher the difference between the energy level, lower will be the wavelength. So that is what we will see from these equations. Similarly, the frequency and difference in energy equations are directly proportional. So it means the higher the energy level difference, the higher the frequency we will have. So I will show you an example of this. So imagine there is E4, E3, E2, E1. These are four energy levels. Okay, each line represents an energy level. Okay, how many emission transitions are possible? Okay, so emission transitions are basically the transition from higher to lower energy level. So I can see that we can draw from each line whatever the possible transition. So from E2 to E1 it is A, from E3 to E1, from E4 to E1. So all those ABC are the three transitions. Then E4 to E2, then E4 to E3, then E3 to E2. So all those are possible transitions. So there are six possible transitions you can see. Okay, and if the question says draw a spectrum of the increasing wavelength, so if I'm drawing increasing wavelength, you will see that the longest difference is E4 to E1. Now, higher the difference, lower would be the wavelength because they are inversely proportional. So you can see that the lowest wavelength will be coming first, that is C. Then you can see that there is the second highest is B, and the difference between the energy levels of E4 and E3 is not that much. So the B and C are very close to each other. Okay. Then we have A, which is next highest, and A has a very higher difference. So there are more spacing between E3 and E2. So there has to be more difference in the wavelength as well. So that's why I drawn A a little bit more further away from B. Similarly, D is much smaller than A. So the next would be D. The E has very slight difference between D and E. So that they are closer to each other. And F is another, the smallest difference. So there will be highest wavelength. So remember that higher the difference in energy, lower would be the wavelength, and the difference in the vertical lines, okay, those lines represents the difference in the wavelength also. You can draw that on the spectrum as well. Okay, now what is a spectrum? So we will first talk about the emission spectrum. So in emission spectrum, when a gas is subjected to a strong electric field, the electrons accelerates through the gas and collides with the electrons of the gas atoms. Okay, now these collisions are inelastic. That is very important. So because of that, the electrons of the gas atoms will gain some energy and they will make an upward transition. Okay, now whenever they make an upward transition, they won't remain in upward higher energy level because they are unstable there. So they will eventually come makes a downward transition, releasing that energy in the form of a photon. Okay, in the form of photon, this energy of the photon has a wavelength. That wavelength corresponds to the difference in energy that as we discussed earlier. Okay, and only those wavelengths will be observed which are outcome of a transition. Okay, so this is what the emission spectrum looks like. So when we have this setup, we see that there is a gas in a tube, glass tube is accelerated. The electrons are accelerated using some high voltage, and then it passes through a prism or grating, okay, which separates out all the wavelengths discretely so that we can see it through it is, and then there is a black background. There is a black or a dark background, and there are colored lines. No, they need not to be a colored line. It is colored only when it is in the visible spectrum of the wavelength, but it is not limited. All the spectrums are not limited to the visible range of the light. It can be some infrared, some can be ultraviolet and other wavelengths as well. So, but we do see the wave like vertical lines because the vertical lines are seen because between the prism and the grating there is some slit that we keep through which the light is made to pass. That's why we see the vertical line because that's why we are only passing through that slit. Okay. So once we do that, so this is how the emission spectrum is created. Now, apart from that, we have absorption spectrum. So in absorption spectrum, what we do, we have a white light source. Now, when I say white light source, it means it has all the wavelengths. Okay, it has wavelengths, specifically all the wavelengths that we can think of. Let's say it has all the wavelengths. Now, when we pass that white light through a cold gas, the cold gas atoms will absorb the wavelengths, which can make transition possible for between any two energy levels for the gas atoms. Okay, let me repeat what I said. The white light will bring all the wavelengths. The gas will only absorb those wavelengths which have that energy, which can make a transition possible between two energy levels for the gas atom. Now, every gas has a different combination of energy levels, different differences between energy levels, and all those possible transitions will be absorbed. Now, what happens is anything that is not absorbed is passed through again a slit and a prism. And what we see is that all the colors of the light, okay, we will see all the colored background, we will see because it will have all the wavelengths, so we will get all the colored background, but there will be some black lines. Now, what does this black line represent? The black line represents the missing wavelength from the white light that are being absorbed by the gas molecules. So this is how an absorption spectrum is obtained. Okay. So what is a spectrum? Spectrum is basically a collection of wavelengths. We can say a collection of energy levels. So this is when we see through a spectrometer or through prism, we get a vertical lines representing each wavelength. Okay. So this is what the spectrum we see. So there are two kinds of spectrum: emission and absorption. Now, if I'm just observing a white light through a prism, I will not get any kind of vertical lines. So that will be a continuous spectrum where we see all the wavelengths. Okay. Now we will try to answer a few questions based on what we learned. Okay, so see how we can apply this concept. In this question, what they are asking is, they are given the 4 energy levels and the wavelengths associated to 4 energy levels. Now, what are the wavelengths of the spectral lines emitted by the gas in order of decreasing frequency? Now, decrease in frequencies, remember that frequency and wavelengths are inversely proportional in this case. So if there is a decrease in frequency, it is equivalent of saying of increasing wavelength. Okay. So increasing wavelength will be what? The one which will be very shortest energy difference will have the highest wavelength. So lambda 3 will have highest because the energy levels are very closer to each other. Okay, likely the second rank one will be lambda 2, then the third will be lambda 1, and then lambda 4 will have since it has the highest difference, it will have the lowest wavelength. So which option matches this? It is B. Okay. Similarly, let's see another question. So here in this question, what they're saying is that a diagram shows the emission spectrum of an atom. So there are like lines which are given. Which of the following model can produce this spectrum? Now see this. Now what will happen? Let's say I will draw all the possible. So there are 6 lines, 1, 2, 3, 4, 5, 6. So there are 6 transitions that are possible. Okay. Now whenever I do something like this, let's say I try this for option number A. Now for A, these are the transitions that are happening that are possible into this. Okay, so let me draw all the possible wavelengths from each. Okay, so these are the 6 possible differences. Now here you can see that this and this has to be same. Okay, so they are very short, so they will have very high wavelength difference, so that is fine. Now then we have 2 wavelengths which are almost of the same length. So I feel this wavelength, let's say this is A and this is B, they have same wavelength, same difference in energy. Okay, so they might be corresponding to these two. And then we have A, which is, and then we have this, let's say this is C and D. This is the longest difference. So C is this is B and A, and this is D, and these are, let's say this is E and F. Okay, so you have to compare the energy levels. How are the transition difference between the energy levels is the same. Okay, so the difference between the energy levels vertically, you can see E and F will have same. Similarly, B and A will have same amount of difference. So this kind of a diagram we have to see the vertical difference, and then this vertical difference will be equivalent of saying this vertical distance. Okay, so we have to compare that, and then we will get the option A is correct for this, which won't be possible for any other level, because we can see that for C, let's say there's only one possible highest level. The next highest will be this. So obviously they are not close to this other, like this. Okay. Similarly for D, this is only one where I will get, and for B it is all equally spaced. So all those transitions should have same wavelength. So A is the correct answer here. You can see. Similarly, let's say they have given the energy levels for this. In joules, they have given 10 to minus 19 and they have given some wavelengths of the spectrum. Now determine the energy of the blue wavelength. Okay. Now, if I want that energy of the photon, now here I have to make a decision whether I want it in electron volts or joule. But since you can see the energy levels as given in joules, it is much more easier to do everything in joules than in electron volt. So I can do this energy. It will be hc by lambda. So hc I will substitute 1.9 into 10 to minus 25 joule meter, and this will be 435 joule meter. Okay, sorry, just meters. So this will cancel out, and we will get our answer. The nanometer is, so we have to multiply this with 10 to minus 9. Yes. Now this will give me the energy of the photon, and that's it. You don't have to do anything extra here. Apart from this, identify which energy level of transition is possible give rise to the photon of this. So let's say we calculate this. and we will get some difference of, let's say, 3.5 or 7. Now you can see that what we need to do is we have to first find this number, and then once we get that value, we have to compare what difference between which two energy levels. So for example, if I take the difference between these two energy levels, so 5.44 and 2.42, it is roughly around 3.02. So if my energy level is 3.02, then these two energy levels are involved to give me this photon. Okay, so this answer turns out to be roughly around 4. So that these two energy levels are much closer. Okay, the differences are roughly around 3.7 or 3.8. So the transition from 0.87 to 5.44, the difference, whatever we will take, that will be our answer for this. Okay, which is roughly around, I think so, this is 4.6 something. So this is also 4.6 into 10 raised to minus 19. So that is the difference. So we have to compare the energy of the photon with the difference in energy levels. And how we can justify that? We have to say that energy of the photon of wavelength 458 nanometers is equivalent to the difference in the energy level. Okay, so this is how we can do this. Okay, one more question like this: outline how the evidence supplied by the Geiger and Marsden supports the nuclear model of the atom. So here we have to just write the observations and the conclusions that we discussed in the beginning of this session, where we say that where most of the atom, most of the alpha particle went straight through. Okay, so that kind of conclusion says that the atom is empty. Okay, so those kind of, so for 4 marks we have to write all the observation and all the conclusions, and then you will get all the 4 marks. Okay, using Geiger and Marsden experiment. Outline why classical physics does not permit a model of electron orbiting the nucleus. Okay, so according to classical model, the electron orbiting the nucleus suggested that the electron is accelerating. Okay, there is some kind of centripetal acceleration, and an accelerating electron will radiate and release energy. Okay, it radiate and release energy. And what will happen to its orbit then? It radiate, release energy, and it will spiral down towards the nucleus. Okay, so that's what. So it will spiral down towards the nucleus like this, and this is where the classical model failed, because there was no radiation that was detected from the electron. There was no spiraling down. All the electrons were orbiting the nucleus at a stable orbit. So this is where the classical model failed. So this is the answer of this question. Okay, so this is all the part of the content we have covered in the SL part.